Hello, everybody. I would like to welcome you on our webinar today. I'm glad that we can meet you at least online. My name is Jan Neumann. I'm a CEO and co-founder of NenoVision company. I will guide you through our webinar today. Our webinar is organized on the occasion of our product launch, our second generation of LiteScope AFM module for SEM. I will be proud to share with you the highlights of our LiteScope 2.0, but also I will talk about the advantages of correlative imaging using AFM in SEM and its applications. Webinar is live, and you are encouraged to raise questions anytime during the webinar via Q&A window. My colleagues will try to answer your question immediately via chat, which is visible for everybody. At the end, I will pick a few of the questions and I will repeat them loudly so all of you can hear that. Be aware that there is about 30 seconds delay due to the broadcasting, so we cannot respond immediately. So about the outline of today's webinar. So yeah, you should see the screen right now. So I will introduce us a bit, and then I will focus to the question why AFM in SEM, why you should be interested, and what are the main advantages. I will talk about the correlative imaging and our technique CPEM. I will introduce the LiteScope 2.0 still X, and I will then highlight some main application field. I will summarize, and there will be space for questions and answers. So, on behalf of NenoVision, I would like to say something about us. So we are located in the Czech Republic, in the Brno. We say it's a heart of the Europe, and Brno is a university city with plenty of exceptional universities and research institutes, and we are a spin-off of one of them, of the CETEC, Central European Institute of Technology. Brno is also quite well known as a center of electron microscopy, and people say that about 30% of the electron microscopes are produced in Brno. It's because of that Thermo Fisher and Tescan are located here. So we are very happy to be in such an innovative and microscopically oriented ecosystem. As you can see, we are quite well related to the university, and we still feel responsibility and touch on the development and discoveries. And so why NenoVision? So we decided to create a unique tools on the top technological level used by the scientific community, driving discoveries with the significant impact. And this is our dream or our mission, how we want to contribute to the global development. I will try to highlight you and convince you that combination and integration of AFM inside the SEM, it makes sense. And I will try to answer the question why AFM in SEM. And before I will talk about it, I just wanted to say or to show you how it looks like in reality. So you see is AFM module LiteScope placed on the SEM stage. So now you can visualize what I will talk about. So it's not extraordinarily complicated. It's quite simple how to put it there. For the integration, we are trying to tackle several issues which we think that rise during the microscopy or generally nanotechnology field. So one of them is the difficulties to do the complex analysis or even more correlative sample analysis at the nanoscale. We also try to help with the issues of inability to do in-situ sample analysis. And we will also focus and tackle the issue with the difficulties with the precise localization of the region of interest. With that, we try to provide the scientists the results and analysis of their sample, which are otherwise unable to acquire or it's extremely complicated. So I will describe a bit AFM, atomic force microscopy, and SEM technology, and all of you know they are based on completely different principles. So atomic force microscope is based on the interaction between the very sharp probe and the sample surface. So what we are talking about is actually touching of the surface of your sample. On the other hand, electron microscopes is based on the interaction of focus beam of electrons with the sample. So when AFM, I'm talking about the touching. With the SEM, I'm talking about the more looking or analyzing by watching. And so to combine and integrate AFM together with the AFM, we are trying to take the best from both of them, from the touching and from watching. So the advantages and strong field of AFM is an extremely precise 3D topography. You can do the mechanical measure mechanical properties, electrical properties, or magnetic properties. What we take from the SEM is a really nice ability to do fast 2D imaging on the wide range of areas with the big view field. But also you can do the chemical analysis, you can do the surface modification, and you can use many other detectors and techniques to analyze your sample. So we take both of them and we introduce you the LiteScope. I would like to point out that actually what we are bringing with the AFM to SEM community. So if we do in-situ AFM analysis, we are talking about the measurements of the mechanical properties. I'm not talking only about the sub-nanometer topography, but we can also analyze the surface roughness, elasticity or hardness of the of your samples, and all of that is locally via mapping. We can also nicely measure the electrical properties, and then we are bringing the possibility to measure the conductive maps, also only with the NenoVision measuring on the insulated areas. We can measure the local surface potential of the IV curves. So here you see the techniques like the CAFM, KPFM, or even the STM. We are quite proud that we can bring also to the in-situ community possibility to measure magnetic properties. So magnetic domains imaging using MFM, and we also can measure the piezoelectric domains using the PFM technique. So what you see is actually quite broad techniques and actually the properties which can be analyzed using the AFM. We are trying to point out the unique application. I will try to express what does it mean or how we understand it. We understand it's when 1 + 1 is not 2, but is 3, which means that when integrated AFM and in SEM gives you more than 2 separated instruments. How we describe that? So the first of all, there are experiments or applications which cannot be done on separated AFM and SEM instrument at all. For example, we talk about the application where both AFM tip and electron beams are used and required simultaneously. Or as an example, for in-situ AFM and SEM analysis, you might, for example, to induce some interaction and directly record the changes by the AFM or by the other techniques. So in operando measurements, there is no other way how to do that without AFM and SEM. And there is another approach when analysis on separated AFM and SEM instruments are extremely difficult, expensive, or time-consuming. So by the end of the day, you would not do that, or it's extremely complicated. To give you the example, so for example, if you need extremely precise correlation of AFM and SEM data, so this is one of the reasons which cannot be done on the separated instruments, or where you really need to precisely find the region of the interest. So if you find a few nanometer size nanoparticle or the periodical structure which you need to be analyzed by the AFM, this is what we call unique application, because you need the integration. And the third part or point is sensitive sample. So if I use a sensitive sample and I modify them inside the electron microscope, I want to use them by the AFM, I just cannot remove it from the vacuum, or it's very complicated. So I hope I give you some examples and idea what we mean if we are talking about unique applications. And I would like to show you 3 areas where we see the highest added value. So what I meant is first of all, the complex sample analysis, and even more the correlative analysis, when we need to correlate and analyze the data from SEM and from the AFM, and it can be plenty of them, and we can do the you need to do the correlative imaging. As an example, I will use 2D materials, molybdenum carbide, which is a fancy 2D materials, as you can see. And if I mean complex analysis, I mean really complex analysis. Using the SEM and AFM, I can analyze the mechanical properties, I can analyze the topography, and I can, for example, analyze the chemical composition using EDX. And you can imagine there could be much more. So this is what I call complex analysis. Regarding molybdenum carbide, actually, it's a nice example because it's a novel material. Its perspective from the clean energy or hydrogen reactions, etc., etc. So once more, using the SEM, I can provide several imaging or imaging techniques like imaging using the secondary electron, backscatter electron, EDX. There might be EDIC and others. I can use AFM. So what you see is the topography. You can see the local elasticity. There could be magnetic properties, electrical properties, etc. And when we are talking about the complex correlative analysis, I'm talking about the stacking and putting all of that together. And because we are using the special multidimensional approach and the CPEM correlation, we can do that in the way it was not possible before. So benefits: extremely precise nanometer precision of correlation of data, and time efficient for complex analysis using SEM and AFM techniques. Second area where we feel very strong and when we think we are bringing the high added value, it's an in-situ analysis. What we mean in-situ, we mean analysis in the same time, in the same place, and under the same conditions. So you are preventing the changes of the contamination of your sample during the transfer. On the right side, you can see the visualization that everything can be used together in the same time. I'm very proud that for this area, Marc, our customer, agreed to become a scientific ambassador and help us to explore the possibilities for in-situ community. I really like when he's claiming our LiteScope as a Swiss Army knife in your SEM, but you can hear him directly.
We are here at the Scientific Center for Optical and Electron Microscopy of the ETH Zurich.
My name is Marc and my business is in-situ electron microscopy. We have recently acquired here at ETH NenoVision AFM. This AFM is running inside the chamber of one of our SEMs, and it enables us to do correlative studies of our materials. We can combine whatever we see in the SEM with whatever the AFM delivers. So we can, for example, of course, look at topology of samples. We can also perform local IV measurements, or we can look at the evolution and propagation of ferroelectric domains as a function of the environment. There's so many things you can do with such an AFM. It's like having a Swiss Army knife inside the chamber of your SEM. If you want to learn more about the capabilities of NenoVision, please have a look at the webinar that is running.
Okay, I'm sorry. I guess the video was stuck. Yeah. So
we are here at the Scientific Center
so let me talk Marc once more again.
My name is Marc and my business is in-situ electron microscopy. We have recently acquired here at ETH NenoVision.
Okay, so hopefully now it will be okay.
This AFM is running inside the chamber of one of our SEMs, and it enables us to do correlative studies of our materials. can combine whatever we see in the SEM with whatever the AFM delivers. So we can, for example, of course, look at topology of samples. We can also perform local IV measurements, or we can look at the evolution and propagation of ferroelectric domains as a function of the environment. There's so many things you can do with such an AFM. It's like having a Swiss Army knife inside the chamber of your SEM. If you want to learn more about the capabilities of NenoVision, please have a look at the webinar that is running on the 4th of February.
Yes. Thank you, Marc, for the introduction. And I will give you also one example from our side. So when I'm talking the in-situ analysis, I will give you the example when it's fundamental to prevent the air exposure of your sample and I will give you the example of, I will say, quite interesting sample and the magnetic nanopatterning. It's a thin film from the iron and nickel, and actually it's a very sensitive and prone to oxidation upon the air exposure. So what's the idea what guys from the CdTe in Brno did? They use a focused ion beam to selectively transform the magnetic properties of such a film. So they are able to convert the thing from the paramagnetic to ferromagnetic to properties, means from FCC to BCC structures. And actually on the SEM images, you can nicely see the contrast. So if you want to analyze it from the topography point of view, there is no way to take it out from a SEM because it will immediately oxidize. Therefore, we are coming with our AFM. Simultaneously, we can record SEM and AFM images. And as you can see, because you are FIB milling, so you are removing the materials, so we can analyze the topography, and even it's not that visible, we are able to analyze a nice profile with 0.5 nanometer height and stepped, which is caused by the difference between FCC and BCC, the structure. Then, of course, we can use a CPEM, a correlative imaging, which means we can visualize together the topography with the electron, with the SEM image, and you can nicely see the contrast coming from the different transformation of the sample. So what's our advantages? The first of all, in-situ combination, that immediately after focus ion beam, we are able to use the AFM, and also easy localization of the region of interest. There will be no way to find it outside the SEM. And the last most important value, which we think we are bringing, is a precise localization of the region of interest. So using a SEM, we can extremely precisely navigate the AFM tip to region of interest. I have a nice video here where you can see the AFM tip, how is coming and how is navigating to specific nanowire, which will be analyzed later on. So this is precision which we can provide. And for that, I would like to show the example on tungsten diselenide flakes light on the silicon nanopillars. So on the picture, on the SEM overview picture, you see that the flakes are just somewhere. And actually what we are searching for is our specific monolayer of the flake lying on the nanopillar, which is designed and which should create a single photon emitter. So without the AFM in the SEM, the navigation is extremely difficult. And using the SEM, we can localize the appropriate structure and then analyze it. So as you can see, if we find the proper structure, we can actually, from the photoluminescence, you can see that there is an emission of the photons. And then I'm interested about the topography of the sample and how the flakes lie on the nanopillar. So I can do the AFM. I can nicely measure the profiles, and then I can also put it together. So I can nicely visualize the individual layers, which colors represent them, but then also the topography, and I see how the flakes is following the substrate. So yes, fast, region of interest localization is extremely important, and also in this case the correlative AFM and SEM imaging. These three ideas you can use in broad range of applications like material science, 2D materials, steels, batteries, ceramics. You know, it's very broad area. Nanostructures, quantum dots, different patternings, when are you using focus on beam or gas injection systems. We have a variety of applications for semiconductors using for integrated circuit or solar cells or MEMS and NEMS, failure analysis, etc. And also it's growing applications for the life sciences, for the cells imaging, proteins and technology, etc. So with that, I would like to conclude the benefits of AFM in SEM. So the first of all, we are extending or enhancing the SEM capabilities. We are bringing the AFM possibilities to the SEM. We offer the ultimate precision of the correlative and complex analysis using this approach. You do not risk any contamination or changes during the analysis on different instruments because we do that in situ. And we offer extremely fast and precise localization of your area of interest. And we are bringing the third dimension for 2D SEM images. So we have a sub-nanometer resolution, which we can add to the SEM. So now I would like to move and talk about the correlative microscopy, and I would like to say a few highlights about this, for me, very promising area. So generally, correlative imaging or microscopy is defined as a sample analysis, but at least two different imaging modalities. Then for correlative imaging, we talk that we try to correlate or traditionally just overlay these images. I will give you the two examples. It's quite famous: Raman imaging and scanning electron microscopy, and CLEM, correlative light and electron microscopy. So the approach is as follows. You make the separated SEM image, then you make a separate Raman image, and then you correlate the data together. It's quite powerful because you can analyze using the Raman chemically your composition, what you see on the SEM. And the same principle is when we talk about the CLEM, correlative light and electron microscopy. So you do the light microscopy, then you do electron microscopy, and you overlay the images, and then you try to combine both techniques together. Nevertheless, this traditional approach has some drawbacks. The first of all, it's a very difficult to precisely find the same region of interest, even more if you want to use multiple techniques. It's extremely time consuming. Also, the data correlation is not that straightforward and as simple, because you have to do really precise image alignment, and you have to restore the distortion of the different images, and then you have a compatibilities like a formats, pixels, resolution, etc., etc. And still you need a dedicated instrument, and you need to have a quite complicated or sophisticated sample transfer. So our solution for that is a unique CPEM technology. I already talked about it a bit, and now I would like to explain in more details how we are approaching this issue and what we are offering additionally. For that, I would like to play a short video which will try to introduce you what we are doing.
The correlative probe and electron microscopy, shortly CPEM, is a novel method of multi-dimensional correlative imaging, enabling simultaneous acquisition of data of the SEM and AFM that can be easily correlated into a 3D image. It eliminates the need for double localization of the region of interest, enables highly precise imaging and alignment, and advanced data correlation. CPEM is made possible by the AFM LiteScope, designed for integration into the scanning electron microscopes and offering an all-in-one solution for the simultaneous analysis of multiple material properties on the nanoscale. During scanning, the electron beam points close to the AFM tip with a constant offset. They both remain static while the sample is moving with LiteScope's piezo scanner. This way, data from both microscopes can be acquired at the same time in the same place and under the same conditions. Simultaneous detection of various SEM and AFM signals enables unique combinations of data, such as topography and material contrast, mechanical or electrical properties, resulting in three-dimensional CPEM images. CPEM enables sample analysis in a way that was difficult or impossible by the two imaging techniques separately and brings new possibilities for advanced correlative imaging in a variety of fields such as material science, nanotechnology, semiconductors, life sciences, and many more.
So this is what we are doing, and this was just overview, and I will try to make sure that you understand. I will go try to explain once more the principle. So the point what we are doing during the CPEM is we focus the electron beam close to the AFM tip. Both of them, they are static, and then we are scanning and moving with the sample, which enable us to simultaneously detect both SEM signals and AFM signals. And because there is a constant offset between E-beam and the AFM tip, it's very simple to just remove this offset and create the so-called CPEM view. This is extremely precise way how we do that. And we actually, once more, we take the best from both of them. We take the AFM topography from the sample, which is extremely precise. Then we take the SEM image with all of the material contrast and features which are there. We put it together, and we end up with the so-called CPEM view, which means XYZ is coming from the AFM, and the color represents the contrast from the electron microscopy. And we can do more. We can do so-called multi-dimensional correlative imaging, because simultaneously we can acquire more signals. And then we can just correlate them, all of them together, just the different layers of one analysis. I want to show you the difference using the CPEM and it's quite visible is on this image, that on the left side you see the AFM, on the right side you see the analysis using the CPEM. Simply to AFM we add the signal and information from the electron microscopy, and this is what we are doing, and I think this is the next step for the imaging. And when I was talking about the multi-dimensional imaging and simultaneous data various of data acquisition, I just wanted to show you from our software. So this is what we do. We set up just the different channels represent the different signals from electron microscope or from the AFM, and then using one scanning system we just acquire all of them together. So simultaneously we acquire AFM topography, signals from the secondary electron, from the backscattered electron. We are measuring simultaneously the local elasticity, and all of that together. So this is what we call real correlative imaging. So using the CPEM, correlative probe and electron microscopy, we are convinced that we are bringing the big step in the correlative imaging. We are enabling simultaneous acquisition of AFM and SEM signals. We are convinced that we are providing more information than each imaging technique separately. This is our unique applications, and it's AFM and SEM. It's all in one and simple to use. Right now, I will be really happy to talk about our next generation LiteScope 2.0. It was launched 1 week ago, and now I will be really happy to share with you the highlights and achievements which we made on this instrument. So here it is, LiteScope 2.0, small, compact, vacuum-compatible AFM module for SEM, ready for correlative complex sample analysis. Again, we have prepared, I think, really nice overview video, so please enjoy it.
The growing need to characterize and analyze structures in the nanometer range and the complexity of such measurements with various instruments create a demand for automated solutions and advanced correlative analysis. That is why we have developed LiteScope, a unique compact atomic force microscope designed for plug-and-play integration into scanning electron microscopes. With LiteScope, you are able to merge the forces of the two of the most used techniques for sample analysis on the nanoscale. Measuring with LiteScope is intuitive and simple, yet precise and time-efficient. Its integration into the SEM prevents sensitive samples from contamination or oxidation, as the measuring is done in the same place and under the same conditions. LiteScope enables precise localization of the region of interest and AFM tip navigation. It extends the capabilities of SEM by measuring a sub-nanometer topography, together with mechanical, electrical, and magnetic properties of the sample. LiteScope incorporates a unique imaging technique called correlative probe and electron microscopy, shortly CPEM, enabling simultaneous acquisition of AFM and SEM data. LiteScope and the CPEM technology allow sample analysis in a way that was difficult or impossible by the two imaging technologies separately. Together they bring new possibilities for advanced correlative imaging in a variety of scientific and industrial fields such as material sciences, nanostructures, semiconductors or solar cells industry, life sciences, and many more, defining their own category of the correlative microscopy.
That's LiteScope 2.0. And so actually what's new? We are talking about the next generation of LiteScope, and actually for several years we were carefully listening the customer needs, and with the LiteScope 2.0 it's our answer. And actually even it does not look like it's a completely redesigned LiteScope number one. So there is a different cabling, different scanner, different preamplifiers in order to get a better performance and provide a faster, smaller, and lighter AFM module for SEM. What is the main difference is a speed of the acquisition. So compared to previous one, we are 4 times faster for the measurements, and we are coming close to the relatively fast SEM measurements, so the times of AFM and SEM are getting similar. The second reason why we did it, it was smaller. So LiteScope 2.0 is 1 centimeter reduced from a previous version, which means we can fit into the much more electron microscope, and also generally the operation is much more comfortable. And the third point is we are 30% lighter. What's the result? That we can fit to any stage which you are using, so you don't have to take care about the weight limitation anymore. I'm happy that's only better. There is no specs or feature degradation, and that's it. So what I think is most important upgrade, it's a fast data acquisition. So right here I'm showing the imaging of the it's a test sample. It was done in 2 minutes. It's speed up to accommodate it for a presentation. The height of the individual step is like 20 nanometers. So you see the quality of the image, and this is taken in 2 minutes. I'm not talking only about the AFM. Of course, you can still do the CPEM and the correlative imaging. So here you can see the real sample, not the test sample. Actually, it's a 2D materials. It's a molybdenum carbide, and this was done within 3 minutes. So together, simultaneously, again, we acquire AFM and SEM. There are just 2 signals, but it can be many more, as you know from my previous slides. And so within 3 minutes, you get the correlative imaging, which enables you to correlate things and come from the 3D topography to CPEM, to correlate everything together fastly and with a high quality. We are not talking only about the speed. We take care also about the resolution and performance. So what I'm showing here is the calibration sample, which is silicon carbide with a nominal step height on the individual terraces with 750 picometers. And using the LiteScope 2.0, we can measure and analyze in that direction in the precision of 50 picometers. So I would say it's a really outstanding performance. And for X and Y, we decided to show the performance on the sample from Sydney Cohem, from the Weizmann Institute of Science, which is Correlative, which is calcium carbide structures, and they are extremely fine. So they are corrugated period about 20-25 nanometers with the height about from 0.3 to 0.6 nanometers, and this is what we have got. So we are really able to provide high resolution in X and Y and also Z directions. And actually, those images were acquired, 2 of them, so the quality is so high that we can even stitch them together. To be honest, it took like a half an hour. So if you want to go for high resolution, you need to wait a bit of more. But the performance of the instrument is really good. Now I would like to talk about the LiteScope setup. So how actually it works. So first of all, you have you locate the LiteScope inside your electron microscopes. Then you have the appropriate features, which are designed for specific SEMs. Then we use our control unit NanoBox, and then you can see our NanoView software. Just if you check, there is just one PC. We don't need any additional PC because our NanoView software is operated with our web browser. So on the normal SEM PC, you just open the web browser, put their IP address, and you can run and operate our software. So it's extremely comfortable. So the package consists of scanning head, control unit NanoBox, control software NanoView, and adaptation and features. So that's a package which we provide all of that together. About some specification, as I mentioned, we reduced the sizes. So currently it's like 12 centimeters or 120 millimeters by 85 millimeters. Height is about 45 millimeters, depending on the sample height. It can operate in the ambient condition or in the vacuum. We claim up to 10 to the minus 5 pascals. The weight is 460 grams, and that's important because it's a less than half kilogram, which is usually the limit for operation of the stage in tilted position. Regarding the scanner, where we modified quite a lot, so we offer quite wide scan range in X and Y direction, 100 by 120 micrometers in the Z direction. And it can be operated in open loop or closed loop, and we can go with the resolution up to 0.2 in X and Y and 0.04 nanometers in Z resolution. So that's basic about specification. On the web pages you can find more details, but I think it's sufficient. What I would like to mention once more, and I'm really proud about it, that we can manage and perform different analyses, and this is what we are bringing to SEM community. So we can measure mechanical properties with all of these topography, surface roughness, elasticity, and sample hardness, etc., etc. We can provide local electrical measurements of different properties like local conductivity, surface potential, or we can measure different IV curves. We can measure magnetic properties using MFM, and we can analyze electromechanical properties using PFM mode. For that, we are using self-sensing and self-actuating probes, which is quite different to standalone SEMs, which are usually using the laser for the detection. So there is no laser, no beam exposure of the laser, and we can work with the variety of them. So the reason why we are using different probes which are already available on the market is that each probe is suitable for different techniques. So for example, Akiyama probe, we use it for the topography or after the modification for the magnetic force measurements. We have developed our probes, we call it nanoprobes, which we use for the conductive measurements like conductive AFM or KPFM. Then we can use a just simple wire for STM or IV curves measurements, or we can use a piezo-resistive probes PRSA for the nano indentation because they have a diamond tips, or for the topography imaging. So, and to be honest, we are capable to cover and work with almost any available self-sensing probes, because what we are changing only is a probe holder. So, and this is a really simple modification. I would like to highlight one more advantage using SEM integration with the LiteScope 2.0 is that we really unified the adaptation mechanism. So currently, as you can see on the picture, we have just one base plate, which is unified for all of the manufacturers, which is mounted on the stage, and that's it. And actually for the test scan customers or test scan users, there is no need to remove the rotation because we reduce the height, and so you don't need to remove the rotation. You just quickly mount it to the rotation of the test scan stages, and it's very easy going. We are offering also some optional accessories. So one of them is, we call it nano case. There is several reasons to use a nano case. One of them is the protection. So you can put it under the protected area. You can evacuate it. So then you can store the system under the vacuum. But it's already passively, there is also already passive anti-vibration system. So it's suitable for use it as a standalone AFM. The cover is transparent, so you can put it directly under any optical microscope, and you can use it in the vacuum or in the ambient condition, or you can put it by the different gases and perform the standalone AFM analysis. We have also the possibilities if you are using load lock system, so we can exchange the probe and also the samples via the load lock, which for some systems is quite useful. We of course offer the variety of different sample holders. We can customly adapt it for your samples. This is very easy, and quite proud to say that we have also nano indentation module. So it's a real nano indenter from Alemnis, which we add to the LiteScope. So then you can make the high quality and quantitative analysis by using the nano indenter, and at the same time you can use the AFM to check the indent using the AFM. So it was a brief overview about the system itself. The web pages, or you have plenty more information, or just ask us. Now I will come back to the main application areas. And as I mentioned, we see mainly 4 of them. Broadest and the most, I would say, common is the material science, where we have plenty of examples for 1D or especially 2D materials, steel, batteries, ceramics, polymer, composites. For all of that, we can offer some advantages, and we have also some reference samples which we already done the measurement. As I mentioned, it's very useful for the nanostructures, because using the nanostructures, you can analyze the topography. So combine FIB with the AFM, it's a straightforward. But then also it can be quantum dots or different nanostructured films or nanopattern surfaces. In the last years, or last 2 years, we are heavily working on the application for a semiconductor industry. So where we are offering solution for integrated circuits, solar cells, MEMS, and basically for failure analysis. where we can do the dopant visualization or current leakage localization. And last but not least, the life science applications, where we can visualize and analyze the different cells or proteins or for the marine biology, etc., etc. So from each group, I will try to pick one example and show them the benefits for that. First, material area, we choose as an example battery research. The reason is that 2D materials, which is mostly used, you have already seen, and battery research is very broad and I would say in these days the very interesting topic. For the application, we cooperate with the BASF, and what we are talking about is a complex in-situ analysis and characterizes of the materials which are used for batteries for charging and discharging, because during this cycle there are changes and we need to analyze them and understand what's going on. So we use lithium nickel dioxide powder, cathode powder, and then we analyze it from the electrical point of view, from the topography point of view, from the chemical composition. So this material represents a really promising cathode material for rechargeable lithium batteries, and it's important, it's tend to immediately oxidize while it's out of the control atmosphere. So in the SEM, we use a vacuum, and it's really important to do it in this way. Otherwise, on the standalone AFM, it's almost impossible to analyze it. This is how it looks like, just to give you the idea. So it's such a powder with the structure on that. On the left image, you can see AFM tip, so you can exactly navigate the area which you like. During the analysis, so what we did? We simultaneously acquired SEM image, we acquired the topography, and we acquired the local conductivity using the AFM. And we also made the EDX map, in this case, not the best quality. What I'm saying is you can complement it exactly the same place using the chemical composition. And using our CPEM approach, then we correlate all informations together. We take a 3D, we correlate it with the information from secondary electron microscope, we correlate it with the conductivity. And this gives you really deep understanding and very nice tool for understanding what's going on with the sample. And there is an idea actually to use an E-beam for charging and discharging the individual particles and study the changes in situ. So what's the benefits which we brought? So you can be sure that you are able to analyze the same identical spot by SEM, AFM, and for example, EDX, and also the fast and nice localization of region of interest, because you might be interested to analyze specific particle, specific area. The second area what I will talk about is nanostructures. And as a mainly used technique for creating nanostructures inside the SEM is a focus ion beam. So I take this example and I would like to show you the advantages. So generally, using the focus ion beam and creating the nanostructures, then AFM is excellent tool to make sure and check the quality of the structures which you fabricated. So you can check the 3D depth profiling, and especially on heterogeneous samples, you know that the FIB milling is not the constant. And also you can analyze the surface roughness, which is quite important for several applications. I took the application where we do the FIB polishing optimization of the surface by using the topography analysis. So the sample is cadmium telluride, which is interesting semiconductor materials. It's promising for different reasons like X-ray or gamma ray detectors or solar cells, but it's sensitive sample. So under the air conditions, it's oxidize and change. So this is the reason why you need to do it in situ. And also the devices fabricated from these materials are are very influenced by the surface roughness. So surface roughness influence the device performance directly. So to make the high quality and best polishing is important point here. So what we are doing using FIB, SEM, and AFM together, that we use a LiteScope AFM to analyze the FIB parameters for polishing. So we create the several different areas using different dose of the ions, and then we sequentially image them by the AFM, or actually it was one image and we just sequentially analyze them. And what the reason is that we want to determine the sputtering rate, which means how fast I'm digging with the FIB to the sample. And also, I would like to optimize the condition to achieve the as low sample roughness as possible. So actually for AFM, it's quite simple. Analyzing each square, I can immediately determine the height or the depth after the FIB milling, and I can immediately calculate the surface roughness. So the result of the analysis is that I can prepare the plot how surface roughness depend on the applied ion dose. And you can see it's quite dramatical function. The reason is that the telluride inclusions are heavily affecting the heterogeneous sputtering of the cadmium, which induce the high surface roughness. So as we have this function, we can estimate the minimum optimal conditions. And also, during the same analysis, I can measure always the depth of after the sputtering, and very nicely and precisely measure the sputtering rate. So what's the result? That I know that the minimum surface roughness is 39 nanometers under condition of after the exposure of ion dose 5.10 to the 16 and whatever. And we exactly determine the sputtering rate as a 2.6 and 10 to the 14 ion centimeter square nanometer. But what I wanted to say, you know exactly after which dose how deep you are on your sample. So we have again the several benefits. It's in situ conditions, fuzzy region of interest, and really high precision, depth and height profiling. I would like to say something about some example for the semiconductor industry, where I will try to focus mainly to failure analysis, because it's very important application in optimization of the variety of semiconductor devices like integrated circuits, solar cells, etc., etc. And I will focus to local conductivity. So on this case, we cooperate with the ON Semiconductor, and within the failure analysis, we are focusing to localization of current leakage in semiconductor devices or visualization of dopants. And generally, we are bringing the effectivity to the analysis to be able to do precisely and fast. So the example is bipolar junction transistor, and where there is just some wrong function, so we need to do the failure analysis and use a local conductivity exactly on the specific place to be able to localize the defect and then change it in the production. So we did the local investigation using AFM to measure the local electrical properties, but it has to be done in the cross section. And so then there is an advantage of the AFM inside the SEM, because you can really nicely navigate the AFM to the region of interest. And then if you are using conductive AFM instead of some traditional wet etching techniques, you eliminate the risk of the contamination, etc., etc. So to prepare the sample for such an analysis, traditionally people are using the chemical etching or FIB etching, which is more convenient inside the SEM, or this visualization or this analysis can be done using the preparation of TEM lamellas. All of that is quite difficult. So bringing the AFM inside the SEM and to have a possibility to do correlative AFM or KPFM, it simplifies the procedure a lot. As you can see on the both picture, using the combination of AFM, focus ion beam, and SEM, it's from our way the optimal tool how to do the failure analysis of such a things, because I can precisely localize. I think I can make a precisely cross section and then immediately in situ conditions analyzed by the AFM. What the result is that you see what you see on the picture is two regions of interest. When we are measuring in the cross section simultaneously SEM, AFM, and the local conductivity. And as you can see in the local conductivity, you can see several different different structures which are not that much visible on the AFM, on the SEM or the AFM. So by the end of the day, we are able to extremely precisely localize certain features using SEM and then electrically characterize them using conductive AFM. And the conductivity maps is reciprocal or tell us something about the dopant concentration, or it can be also used the similar way to localize the current leakage, for example. So on this point, I would like to again highlight that the huge advantage using the AFM in SEM is a easy localization of the region of interest, and then really fast conductivity mapping in situ conditions. Here it's bringing me to the last application area, which is a life science application. And here we choose the protein analysis, protein nanowire analysis. So what's about that? Colleagues in KTH in the Stockholm, they had a silk nanowire, and they are interested about the analysis of mechanical properties of this natural polymer. So what we can do and offer on the first point of view, we can visualize and analyze the dimensions and give a much better idea how the nanowire looks like. So again, here using the SEM, using the AFM and SEM simultaneously, we are bringing this 3D very precise representation of the nanowire. But then we can also start real mechanical analysis. How we do that? We take the protein nanowire and put it on the supported structures, and then we can use a precise navigation of AFM tip to just push and pull to the nanowire. So what you see on the picture is that how the tip is pushing to the nanowire, and simultaneously we are measuring the force distance curves. So with this, you can really nicely measure the Young modulus of the materials. You can also measure the ultimate tensile strength, but of course you can also analyze the dimensions. I'm sorry we did not put there any real numbers because the publication is still in the process. So again, some benefits: precise localization of region of interest, then analysis of mechanical properties, and complex analysis using the CPEM. So with that, I would like to summarize the webinar. I hope that I was able to clearly present the LiteScope 2.0 as a high-speed, compact, and easy-to-use AFM in the SEM. I hope that I was able to convince you that in-situ analysis of the AFM and SEM enable complex surface characterization, and there is plenty of added value for your research. I wanted to show you that correlative probe and electron microscopy, our CPEM approach, is a real next level of correlative imaging with the simultaneous data acquisition, which is really important, I would say. And I hope that we present our unique applications and trying to show you that there are applications which cannot be done without using on the standalone systems. So we are bringing really something new, and we are bringing the new possibilities to analyze the samples better. By the end, I was trying to show you some examples of where we see the main application fields. material science, nanostructures, semiconductors, and life science businesses. So with that, I would like to thank you very much for your attention. And I see there were plenty of questions during my talk, so I will wait for my colleagues, and they select and picked some of the questions. So I will read it for you, or maybe even comment it. Yep, it's coming. So in the meantime, I have to say there was almost 200 registered participants, so I'm really happy that in this specific COVID period, you are interested in the science still. So yes, I have some questions. So yeah, I'm here back alive. So one of the question is, what exactly in-situ measurement mean in the context of AFM in SEM concept? What is unique about it? So if it was not clear, so in-situ, it means that we use several techniques together in the same time. For example, yeah, so for characterization, so there is no need for the venting the chamber if I want to use AFM and SEM. And in-situ, it means that I'm still analyzing the same things on the same place in the same time. I'm sorry, I'm not sure if I was clear too much. Yeah, so what is the best resolution you can get in the X, Y, and Z axis, and what's the probe to recommendation to get the best resolution? Yes, so we have a 0.2 by 0.2 nanometer resolution X and Y direction. In the Z direction, it's 0.04 nanometers, so 0.4 angstroms. And for the best resolution, yeah, we usually use the Akiyama probe, which is standard and sufficient. This is how we got the results which I was presenting. There is one question concerning how fast is the installation of LiteScope into the SEM. So it's very fast and straightforward. Usually people keep the flanges or inside the SEM, and so it's like 5 minutes just to take it, mount it to the stage, tied it with few screws, and plug the lemon connector. So it's really few minutes. If you finish your job, you take the LiteScope out, so you do not occupy SEM at all, and then in the meantime you can use SEM LiteScope as a standalone AFM. So this is really straightforward. I have a question. What is the maximum weight and size that you can place of the sample which you can place on the scanner? So maximum weight is, we say, 100 grams, but 100 grams, and the area where we are able to scan is like 2 centimeters by 1 centimeter. Yeah, sample might be larger, but just the area where you are able to scan is 2.1 centimeter. What I would like to point out regarding the weight, that heavier sample usually means you should scan slower. The speed has to be reduced, and the maximum to do not destroy the scanner, we say 100 grams, which I would say is quite a lot. So here is one more. Hello, I want to. In new version, you have a possibility to measure in contact mode and perfect union mode. What are the sharpest cantilever available now? Thank you. Yes, in contact mode, we can use Akiyama, as I mentioned, or this PRSI. probes. What's the sharpest? Usually the diameter like 10, 15 nanometers. If you, these are commercially available. If you really want something extraordinary, you can use a FIB to just make it even sharper, or we can do it for you. Then I think we reach somewhere about 6 nanometer in the radius. Yeah. PFQNM mode, I'm not sure. Maybe it's a peak force from the Bruker. So currently, no, we don't have such a mode. I think it's anyway protected by patent. And is it compatible with any SEM? Okay, so we have got the compatibility. So what is the main limiting aspect of the compatibility is the size of the chamber. So this is the reason why we make it smaller. To be honest, there is no other reason for the limitations. So we can use it can be operated in environment SEM, high vacuum SEM. So this is really not limiting. Usually the size is the biggest deal. And then we have options for the immersion objectives, field-free objectives. So all of that we are ready and we are compatible. Yeah, we are in Brno, so we tested with the colleagues here. So this is not issue. I have one other question. How fast? Okay, now I got this one. Yeah. So yeah, I would say that's it. And with that, please, if you are interested, keep going with the questions. Just don't send it to the Q&A. Send it to our emails. Please go to our web pages where you can find plenty of materials, videos, previous webinars, and please get us into the contact. You can find us on www.nenovision.com or check us on the LinkedIn where we are quite active. Please get in touch and we will be really happy to show more what we have in our shelves. Thank you very much for your attention. I wish you have a nice day. Stay healthy and come back to us. Thank you.